Hello, this is our team's entry for the InnovateFPGA North America contest team number AS003. The title of our project is A Mind Reading and Intervention System. The importance of this study is universal, as sleep is important for normal, healthy function for everyone. According to the National Institute of Neurological Disorders and Stroke, about 40 million people in the United States suffer from chronic long-term sleep disorders each year, and an additional 20 million people experience occasional sleep problems. This number is very likely underreported, as many people who have sleep disorders may not be aware of it and may not report it. In addition, it is not only people in the United States who suffer from sleep disorders, but people across the world. The nuances of sleep disorders are very complicated and are generally classified into one of three categories, including lack of sleep, disturbed sleep, and excessive sleep. And because it is difficult to classify these disorders without very strict monitoring, identifying patterns and signals in order to identify and diagnose participants' sleep disorder is very important to classifying their disorders. In order to treat very severe sleep disorders, oftentimes practitioners rely on medications or machines or even more invasive equipment for their patients. Our study attempts to use a sleep-inducing principle using artificial intelligence and various techniques in order to induce healthy and high-quality sleep without medications or other invasive interventions. And so generally, the brain waves reflect the brain activity of any given individual. And during the awake phase, the majority of brain waves are gamma waves. During the time when an individual starts to feel drowsy, the majority of the waves are alpha waves. During light sleep, the majority are theta waves, and during deep sleep, we see these higher amplitude delta waves. What our project proposes in the quest for inducing healthy and high quality sleep at a faster rate is to create a sound from the frequency of deep sleep waves, or the delta waves, the high amplitude and low frequency waves that we associate with deep sleep. And this sound is at a frequency that is intended to induce healthier sleep by lowering the frequency of brain waves and inducing the delta waves that we associate with deep sleep. In contrast to certain other studies that have also attempted to use sounds at certain frequencies in order to induce high quality sleep, our project also uses a more holistic approach, borrowing from methods from meditation in order to allow the user to have a more active experience of trying to induce high quality sleep in a more biofeedback sort of cycle. And so the user will also be engaged in a triad of these three techniques. So first, in engaging in an auspicious lying posture of repose that is intended to relax the user and allow the user to engage in sleep more efficiently. Certain chanting of certain syllables that also helps to relax the mind, as well as soothing music. Our project uses artificial intelligence in order to read the output from electroencephalography, or EEG, which is roughly a measurement of brain waves as brain potentials emitted by activities from the brain. There are 3 physical components of our setup. This involves, firstly, an FPGA board, and this is the DE10 model, which will interplay with the mobile phone that the user will be able to select and interact with, and also an EEG headset that will actually take the recordings of the brain waves. And so the information from the brain waves will be transmitted to the mobile phone through a Bluetooth module, and the FPGA board will be involved in the machine learning and data processing and will feed back these classification results to the mobile phone as well. And so the mobile phone will really serve as the nexus of interplay between the processing and the input of data from the EEG headset. In addition, the mobile phone will be interfacing with the user in order to play the sounds and the music, and also to give feedback to the user in terms of engaging actively in the biofeedback techniques that we discussed earlier, derived from meditation.
The data processing method is as follows. First, the EEG data is filtered or decomposed using ensemble empirical mode decomposition, or EEMD. Then features are extracted from the data which are used to train and build a model. And before building the model, the features are normalized. Specifically, the EEMD used during data processing is used to remove the low frequency drift. This means that the original EEG wave is separated into different components with different frequencies, and the lowest frequency component is then removed because it is an artifact. After the data processing, 20 features will be extracted from the data using functions from the module PyEEG. These features will be then used to train and classify a model. The 3 models that we will be building are the DNN model, the Keras model, and the XPG model. After the models are built, they undergo majority voting to ensure that the highest accuracy is achieved within the models. This graph shows the results of the model voting after using different methods of data processing. The graph shows that we can achieve a stable 85% accuracy a majority of the time. Here are the pictures for the DNN model and the Keras model. And here's the picture for the XGB boost tree.
These are the main components of the project: the electrodes, the headband, the microbit, which will receive data from the electrodes, the Android app, which will receive data from the microbit, and the DE10, which will receive data from the app, performing calculations and send them back to the app. We will turn on the DE10. We can connect these electrodes. The DE10 will be running a server locally. This is the home page. We will create an account and upload files to it. We will sign out of the account and sign in using the app. can turn the microbit on. The first screen will prompt the user to lay in the auspicious position. Proceeding, the app will automatically connect to the microbit, begin receiving data. We will position the electrodes on the forehead. And once the electrodes are positioned, you could view the images, and then you will push record, and it'll begin recording data, and you can look at the sleep state, and the app will begin playing music. It'll also have the sleep sound, which is isochronic noise at 1 Hz, playing in the background. And the app will respond, the server will send data to the app with the awake, light sleep, and deep sleep stages. You can pause and go back to the images. And if you would like, you can upload the file uploads. After using the app, you can sign back in. And the files will be saved, the raw files will be saved in the user, and you can view the image that was uploaded. From the phone app. And when you're done, you sign out.
This log shows the recorded events of interactions between the DE10 server and the mobile application, which occur when the mobile application uploads or downloads files. And the information that is recorded with these events are the user ID, the file ID, the type of interaction, the file name of the file, and the timestamps. This log shows the events that occurred during one intervention session of the eSleep system and the corresponding response times that the server gives. The mobile application sends one data file to the DE10 server every second. And since the server responds on roughly an average between 1 and 3 seconds, this means that the user using the mobile application will feel very small delay, and the process will be very smooth. And this is why the FPGA DE10 server is a very efficient server in our system.